So far we've seen the perceptron algorithm, which only works for linearly separable data and which corresponds to only one neuron. To go further, we need also to be able to train the model properly, that is to find the optimal weights and biases even when the data are not linearly separable. The first attempt to do so was in 1959. The corresponding networks were named Adaline for adaptive linear elements and Madaline for multiple Adaline. Madaline was the first network applied to solve real-world problems. So first, let us look at Adaline. You see on the left the input layer composed of switches that can take values -1 or 1. Then you have potentiometers that correspond to the weights of the network. A bias is also added. Then this sum is transmitted to the -1, 1 function, which gives the final output. So, as you can notice, this is exactly the same model as a McCulloch and Pitts neuron. The improvement lies in the manner the parameters of the network are trained. Remember that this network is impossible to train as such, because the decision function here is piecewise constant. So any gradient-based procedure which relies on the gradient of the loss and thus on the gradient of the decision function won't succeed, the gradient of the decision function being 0 almost everywhere. The trick here is not to look at the output and try to minimize a loss based on the -1, 1 function, but rather to consider the input of this function, namely the weighted sum plus the bias. Note that before the -1, 1 function, you have a vertical line which corresponds to the loss that is computed. What we compute here is a square difference between the weighted sum and -1 or 1, depending on whether the true label of the observation is -1 or 1. So for example, if the label of the observation is 1, you are going to compute the square difference between the weighted sum of the input plus a bias and 1. Contrary to the previous decision function, which was piecewise constant, this loss function is differentiable with a non-zero derivative. Thus, we can use any gradient-based method to optimize it. To summarize, the trick here is not to optimize the loss based on the output of the neuron, but to look at the weighted sum, what is before the final activation function, compute a loss based on this weighted sum, and optimize this differentiable loss, which has a non-zero derivative. So basically, we have changed the optimization problem so that we can apply a gradient-based method to it. Here you see the more complex Madaline architecture in which each element is an Adaline structure. The optimization process in Madaline is quite complex. You can look at the above reference if you want to know more about it. This model or algorithm was originally used for specific applications like speech or pattern recognition, weather forecasting, adaptive filtering, and adaptive signal processing. Note that these applications are still active areas of research nowadays. However, we are now able to achieve far better performances than the one accessible 30 years ago. Now let's look at a simple neural network architecture. We start with some notations. There is the input layer here composed of 3 variables, x1, x2, x3. Then you have one hidden layer composed of 2 neurons, and you have one output layer composed of 1 neuron only. Between each layer there are connections, and usually each neuron of each layer is connected to each neuron of the next layer. You do not have any direct connections between a neuron of the first layer and a neuron of the output layer. You also do not have connections between neurons in the same layer. A specific bias is associated to each neuron. One neuron equals one bias plus a set of weights. The output of each neuron is denoted by A, and the weighted sum, which serves as input of one neuron, is denoted by Z, with a relation A equals sigma Z, where sigma is the activation function. Note that here the exponent stands for the layer and the indices I, j correspond to the neuron I of the next layer and the neuron j of the previous layer. This notation may seem counterintuitive, but it will ease mathematical formulation. You can specify different activation functions for each layer, but inside a layer, the same activation function is used. We will see in the next lecture many examples of activation functions. When dealing with neural networks, we store the weights between 2 layers in a big matrix so that in one matrix multiplication, we are able to compute the set of outputs of all neurons in the next layer. Now that we have mastered the notations, let us consider a more complex network. A question remains: how can we find the weights and the biases associated to this neural network? The perceptron algorithm does not work, since this network contains more than one neuron perceptron and the data are not linearly separable. We could use a routine of Madeline, but there is no convergence guarantees, and it works only for discrete inputs and outputs. So we need to figure out a way to train this network, that is to find nearly optimal weights and biases. We are going to do that using backpropagation and gradient descent.